The chapter 2 of the textbook is related to stress, stress and strain under axial loading. We have already discussed about stress in chapter number 1. It is the internal resistive forces per unit area against external forces. Now we will discuss strain. We have already discussed about axial loading. Axial loading is actually centric loading. If a load is passing through the centroidal axis of a body, it is axial load. If the body is prismatic, homogeneous and isotropic. In this chapter we will discuss some of the topics. The main topics have been mentioned in this slide. What is normal strain? Normal strain is a result of change in normal strain is a result of normal stress. It is actually change in length, either extension or compression. The change in length, if we denote change in length with delta and the original length with L, the ratio of change in length per unit original length is normal strain. If the change in length is tensile, the normal strain will be positive, and if it is compressive, it means decrease in length, then it will be negative. Since normal strain is a ratio between two similar quantities, deformation and length, they both have same units, meters over meter or inch over inch, so the strain has no units. Okay. Since we have established that strain is deformation per unit length, so does it depend upon length? If we increase the length of a bar, will the strain increase or will it decrease? There is a confusion among some people. If we do not change the material and if the stress is kept constant, there will be no change in the total strain even if we increase or decrease the length of the bar. For example, in this case, we have a bar of length L. Load P has been applied on a cross-section area A. If the deformation is delta, stress will be P over A and strain will be delta over L. Now if we increase the area, if we double it and also we double the load, the total stress will be same, 2P over 2A, so it will be P over A. If the initial length was L, the change in length will be delta. This is understood. Total strain will remain the same because the stress is same and the material is same. We are not changing the material. If we keep the stress same but we double the length, for example, if area and load are the same, stress will be again P over A. If we double the length, remember that the deformation will be doubled automatically. So it depends upon material and stress. Stress is same, so it will be 2 delta over 2L. So finally strain will be delta over L. So it is established that if the stress level is kept constant, the strain in a material will remain the same despite of the increase or decrease in length. So strain does not depend upon length of the bar. It depends upon stress and material properties. Okay. Now we are moving towards the next topic, Hooke's law. All deformable materials deformed under loads. This is understood. A material is said to be elastic if it returns to its original position after removal of the load. For example, we have a bar and we apply load P, tensile load. The length of the bar will increase, and after the removal of the load, this change in length, if this change in length disappears, the material returns back to its original length here. it is called an elastic material, are loaded into the up to the elastic range. So in the elastic materials, stress is proportional to strain. Even in the ductile materials, non-elastic materials, within the elastic range, stress is proportional to strain. Stress and strain have linear relationship within the elastic range. So the relationship between stress and strain becomes E epsilon. Sigma is equal to E epsilon, where E is the modulus of elasticity. So E is actually slope of this line, the curve between stress and strain within the elastic region. If the load exceeds the elastic limit, this range does not define elasticity, and Hooke's law is not applicable in this region. It is only applicable when stress and strain are linearly proportional. Okay, how we can find the relationship between stress and strain? We can draw a graph between stress and strain. This is a very important graph, stress strain curve. How we can do it? We can simply test material specimens in a tensile test machine or universal testing machine. In this diagram, you can see a machine which can test tensile properties of materials. Here is a specimen. This specimen is round in shape. We can see that ends of the specimen are threaded, this end and this end. The threads are for the purpose to be held in the machine. This specimen is held in the machine. The threads offer resistance so that when we apply forces, tensile or compressive, the specimen does not get slipped in the machine jaws. So the gripping portions are threaded. Then the middle portion between 2 points where the specimen has constant cross-sectional area, we have pointed out, or we have drawn 2 points here. The length between the 2 points, initial length is L. After applying load, if this L is increased, we can find strain from the length by dividing the change in length over the total length. The machine will just simply give us load deformation values. The load is divided by area and deformation is divided by length to find stress and strain. And then we can draw stress strain curve. Remember that stress depends upon strain. Mostly the people get confused that the strain depends upon stress, but it is not right. Stress depends upon strain, because if we elongate a material up to specific limit, the material will resist to this elongation internally. That internal resistance is stress. So if we do not elongate or compress a material, there will be no internal resistance. So internal resistance of a material always exists as a result of external deformations. So this change in length or increase in length or decrease in length. So this internal resistance exists, this which is called stress, and it depends upon the elongation or the strain. Okay, initially when the specimen is held in the machine, when there is no strain, there is no stress, no internal resistance. As soon as the external load is increased, the specimen gets deformed. With the increase in deformation or increase in strain, the stress increases. Initially, they are linearly related. This increase in stress is linearly related to strain. At some point, this linear proportionality between stress and strain, or stress equal to E strain, this linear relationship exists until proportional limit. Proportional limit. Proportional limit is a point until which stress is linearly proportional to strain. And then after proportional limit, immediately comes another limit which is called elastic limit. Up till elastic limit, elasticity in the material exists. If we unload the material before elastic limit, it will return to its original position. So elastic limit comes after proportional limit. Elastic limit is usually greater than proportional limit, but these two values are so close to each other that usually we consider elastic limit and proportional limit the same value. After elastic limit, there comes yield point. The yield point again is very close to elastic limit and proportional limit, and mostly these 3 points are considered as same. First comes upper yield point, and then the graph suddenly falls down, even though that the strain is increasing, but the stress is noticed to be decreased here up to some point which is called lower yield. The stress level decreases between upper and lower yield in ductile material. Actually, we are drawing this graph for ductile materials. This decrease in stress despite the increase in strain is due to the change in equilibrium state of the atomic structure of the material. The atomic structure of the material, which is usually the atoms are usually bonded together. When we disturb them and apply force on them, they resist to the external forces, resist to the deformation. This resistance is actually stress. After upper yield point, there is a change in internal structure, the equilibrium of the internal structure. The layers of the atoms slip upon each other. This slip actually gives rise to another state of equilibrium. The state of equilibrium, the atomic structure from one state of equilibrium goes to another state of equilibrium. Between the transition state between during the transition between the equilibrium stages, the material cannot offer resistance to external loads. If it cannot offer resistance to the external loads, so the stress level decreases for a moment, and after achieving the new equilibrium stage, the previous equilibrium stage was at upper yield point, the new one is at lower yield point. After achieving new equilibrium state, new equilibrium configuration at atomic level, the material starts offering resistance to external forces again and again. The value of stress increases until a maximum value, which is called ultimate stress. The ultimate stress is the maximum strength of the material. It cannot bear any more load after ultimate stress. Okay, after this, the material cannot resist to the external loads anymore, and the stress level starts decreasing again because it cannot resist to the external forces. If there is no resistance, no internal resistance to the external forces, the stress will decrease. Okay, this after decrease in stress for a moment, and then the material gets rupture. This is rupture strength. Okay, initially this region is elastic region, where the material can return to its original position after removal of the load. Between the upper and lower yield is yielding region, where the material adopts a new state of equilibrium at atomic level, and a permanent the material moves from elastic region to plastic region. Yielding is a transition between elastic and plastic deformation. After yielding, then there is a plastic deformation region. This plastic deformation region is called strain hardening or cold working region. Strain hardening means change in the shape of a material without applying any heat. So it is also called cold working. And after ultimate strength, up until the rupture strength, the material undergoes necking. What is necking? Necking is simply decrease in the cross-sectional area, gradual decrease in the cross-sectional area of a ductile material before fracture. You can see here in the diagram a neck in the middle of the specimen. As soon as the diameter or the cross-sectional area of the specimen decreases, suddenly after some time the material gets fractured in two pieces. The structure can be seen here. It is a cup and cone shape. This is cone and this is cup. The cup is a concave surface and cone is a convex surface. Ductile materials usually break in this manner. Okay, coming back here. Here we can see that in the necking region, the stress is getting decreased. Why is it getting decreased? We know that stress is equal to force per unit area. While necking, the cross-sectional area gets decreased gradually. If area is decreasing, the stress must increase. But in the diagram, we can see the stress is getting decreased between sigma ultimate and sigma rupture. So this actual decrease in stress level in the diagram is against the mathematical expression where stress is inversely proportional to area. During necking, the area gets decreased, so the stress must increase. There is a conflict. Actually, as per this formula, this diagram should go like this. The stress should increase. This one is called true stress strain curve, and the other one, this one is engineering stress strain curve. As per this formula, if the area is decreasing, stress should increase, which is shown in the true stress strain curve. But since the material cannot resist, so if there is no internal resistance to the external forces, there will be no stress, even though the strain exists. Okay, in the necking region, we can see that the area in the neck region is decreasing continuously. This decrease in area is actually another type of strain. It is decreasing in the lateral direction, in the transverse direction. Although the load has been applied as an axial load, but area is decreasing parallel to the area. Sorry, the area is decreasing in the transverse direction. This decrease in the transverse direction, we see it here like if there is a strain in this direction, there is a force or there is a stress in this direction, in the transverse direction. So we can see that this force is parallel to the cross-sectional area. If this force is parallel to the cross-sectional area, it means there exists shear stress in the necking region. So mostly the ductile materials fail due to shear stress at the end in the necking region. Even though the external force is tensile in the nature, it is normal stress, but in the necking region, the material suffers from shear failure. Some materials do not exhibit such details like proportional limit, elastic limit, upper and lower yield separately. Some of the ductile materials have this kind of stress strain curve where we cannot recognize or differentiate between elastic limit, proportional limit and yield limit separately. Because elastic limit, yield limit and proportional limit are very near to each other, they are considered as same point mostly. But for your understanding, I have drawn a detailed diagram here. If we have a brittle material, brittle materials do not exhibit yielding or permanent deformation. So there is only a an elastic curve, and then an ultimate stress and rupture stress. They both are same. There is no necking in brittle materials. There is no yielding in brittle materials. There is only an elastic elongation or compression in brittle materials. The slope of the initial stress strain curve in both cases is modulus of elasticity. Okay, so the curve for the stress strain curve for brittle materials is very simple. There is no true stress strain and no engineering stress strain curve. There is a single curve where the curve starts from 0 to ultimate and rupture strength. Okay. The brittle materials usually fail in a planar manner. There is no cup and cone shape. There is no necking in brittle materials. Okay. We move forward. This diagram shows stress strain curve for iron and different grades of steel. The first one is, for example, for pure iron, and then carbon steel A36, then high strength low alloy steel A992, then quenched tempered alloy steel A709. We can see for all of them the yield strength and the ultimate strength are different. For example, here is yield strength for pure iron, then for carbon steel, then for high strength low alloy steel, and then quenched tempered. The yield strength has been increased consistently due to heat treatment processes and alloying processes. We can see the ultimate strength also, it is different for different grades of steels and different after different heat pre-treatment and alloying processes. But we can see that the slope of the initial line, this line, it is same for all of these steel materials. If the slope is same, it means E is same. Modulus of elasticity is same. Modulus of elasticity is slope of the stress strain curve in the elastic region. So slope of the initial line is same for all kind of steel, iron grades here. Either they have been alloyed or they have been heat treated. E is same, but strength is different. So it means strength can be affected or can be changed by alloying, heat treating and manufacturing processes. But E, modulus of elasticity or stiffness, cannot be changed. E cannot be changed using these processes only: alloying, heat treating and manufacturing processes. Okay, if now now we have to study the difference between elastic and plastic behavior of material. By seeing the stress strain diagram, we know that there is a initial elastic region between point A and point B. After B, the plasticity starts, and this point C is in the plastic region. If the strain disappears when the stress is removed, the material is said to behave elastic. Between point A and B, if we remove stress anywhere or load anywhere, this material will come back, it will follow the initial path, it will come back to 0 where it was initially. So there will be 0 strain if we remove the load within the elastic limit, and the material is said to behave elastically. The largest stress for which this occurs is called elastic limit. So here somewhere near point B, there will be a value of stress below which the material will exhibit elasticity, and the point beyond which the material does not exhibit elasticity or elastic properties is called elastic limit. So when the strain does not return to 0 after the stress is removed, the material is said to behave plastic. Somewhere in the plastic region beyond point B, for example at point C, if we unload the material, it will return to another point, point D. At point D, strain is not equal to 0. So it means there is some permanent deformation in the material. If there is permanent deformation in the material, so this point C exists in the plastic region, and the material is behaving plastically in this region. So it is clear that if the material is coming back to its original position, original shape, after removal of the load, it behaves elastically, and otherwise it is behaving plastically. That point where this transition exists, it is called elastic limit or even yield limit. Okay, then another topic is fatigue. Previously we have studied stress strain curves. We know that there are three types of failure in a material under static loading. The material may either get elastically deformed in the elastic region. Elastic deformation is a kind of failure. Then the next type of failure is plastic deformation. In the plastic region, the material gets permanently deformed, and this permanent deformation is another type of failure. And after plastic deformation, the final failure is rupture or fracture, which is ultimate failure. So there is a difference between fracture and failure. Failure is not necessarily a fracture. It can be a permanent deformation, or it can be a temporary deformation in the material shape. And the final failure is fracture, definitely. Okay, if we assume that if we think like we do not exceed the yield strength of a material, if we do not exceed load beyond the yield strength, we think that the material will not fail. It will simply deform elastically, and after we remove the load, it will come back to its original position. So most of the designers think that material will not fail if we do not exceed the loads beyond yield strength. But if the loads are repeated loads, or they are cyclic loads, if the material may fail even before the yield limit, which is sometimes unpredictable. So then comes fatigue properties of the material. Fatigue means failure of material under repeated loads, under alternative loads below the yield strength of the material. So for that we draw SN diagrams. S stands for stress and N stands for number of cycles of load. The horizontal axis of this diagram shows number of cycles of the load. They are mostly in thousands or millions or billions. In 10 power, it is logarithmic scale. 10 power 3, 10 power 4, 10 power 5, up to 10 power 9 or more. This is N, number of cycles of load. And the vertical axis shows stress S in KSIs or megapascals. So at these graphs for steel or aluminium, they are SN curves for steel and aluminum. This graph shows failure values of the values of stress at which material will fail at some specific number of loading cycles. For example, at 10 power 4 number of loading cycles, the aluminium 2024 will fail at this value of stress, which is almost around 44 or 45 KSI. At 10 power 7 cycles, this aluminum will fail at around 22 KSI. Similarly, if we increase the number of loading cycles, the material will fail at lower values of stresses. And for smaller number of loading cycles, the material will bear higher stresses. Okay, if we look at the steel 1020 HR material here, the curve gets flat after a certain value of stress, like this one. So whatever the number of loading cycles are, this steel material will not fail below this stress. For example, this curve is getting flat at 30 KSI. So whatever the number of loading cycles are, the steel 1020 HR will not fail below 30 KSI. For example, at 10 KSI, if we draw a line here, it will never intersect this line. So this 10 KSI is below 30 KSI, and the steel 1020 HR will never fail at 10 KSI even at infinite number of loading cycles. This is theoretically correct. Okay, so this value of 30 KSI, where the SN curve got flat horizontally, this 30 KSI is endurance limit or fatigue limit for the steel 1020 HR. Below endurance limit, the material will never fail at any number of loading cycles. So endurance limit is a very important value for materials under fatigue loading. Just like yield limit was important for tensile loading or static loading. So under fatigue loading, the users or the designers recommend not to exceed the endurance limit of the material or the fatigue limit of the material. Okay. Now deformation under axial loading. We have to derive an expression for deformation delta under axial loading. If we have a bar A and BC of initial length L, cross-sectional area A, and it is under load P. The change in length is delta. We know that as per the Hooke's law, in the elastic region, stress is equal to E into strain. Stress is equal to load over area and strain is equal to deformation per unit length. We put these two expressions in the initial expression of Hooke's law. It becomes P over A is equal to E into delta over L. If we rearrange this expression, the delta can be calculated as P L over A E. So deformation under axial loading will be calculated using this expression throughout the chapter. The deformation, as per this expression, the deformation depends upon load P, length and area. Length and area both are geometry, and E is material property. So deformation depends upon load, geometry, and material property. Okay. This expression of deformation is for a single bar of any cross-sectional area and length under a load P. If we for a single material, if we have another type of bar where either area is changing, our load is changing, our material is changing. For example, this one, where area is changing with the length is L1 and L2, two lengths, area 1 and area 2. Or even if load is changing here, P1 and P2, or if material is different for different lengths. For example, this is material 1 and this is material 2. So we have to find deformation, total deformation, as a sum of segmental deformations. We have to find deformation in each length L1 and L2, and then we can add them up. So the net deformation will be summation of individual deformations Pi, Li, Ai and Ei, where I is number of segments, like it can be segment 1, segment 2, segment 3 and so on. These segments are these lengths change as per change in area or change in load or change in material properties. So we will solve some numerical problem on this topic. Currently I will solve an example problem, solve example from the exercise, from the book, sample problem, and then we will solve some from the exercise later. Here's example 2.01. Determine the deformation of the steel rod shown under the given loads. The steel rod has two different diameters. Here small d is equal to 0.618 inches and the capital D, this diameter, is 1.07 inches. E is same for both the portions, which is 29 into 10 power 6 psi. Loads are different. At the end, there's 30 kilopounds, then 45, then 75 kilopounds. We have to find the total deformation of the steel rod, delta. First, we have to divide this steel bar in different portions to find load in different sections. Because there are 3 loads, we have to section this rod in different sections between each 2 loads, and after each change in area, and after each change in load. Also, after each change in material. There is no change in the material, so we have to section the rod after change in loads and change in areas. So we will start from the free end. This end we will first produce a section here. Then an area is changed, but also load has been changed. So we have to create a section here. And then another load has been changed at 75 kilopounds, and we have to create section here. 3 sections we have to create. Section 1, section 2, and section 3. And we have to find internal forces in these 3 sections. Because area is known, it is external. Length of each section is known, it is external. We have E is known for each section, but load P is internal. So we have to find internal loads in each section. Okay, after sectioning the rod at position 1, and we have to draw a free body diagram where there is a reaction force P1 at section 1. By applying equation of equilibrium, summation of forces is equal to 0. So P1 plus 45 minus 75 minus 30 is equal to 0. Because P1 and 45 are in the same direction, so I have kept them. I have kept a positive sign with them. 75 and 30 are in the opposite direction, so I have kept a negative sign with them. So P1 becomes 60 into 10 power 3 pounds, or 60 kilopounds. Similarly, at section 2, we have to consider the portion with free end. Here is a free end at end D, and A is fixed actually. So where we have sectioned the beam at section 2, the bar at section 2, there is a reaction force P2. Again, summation of forces is equal to 0. So P2 plus 45 minus 30 is equal to 0. So P2 is minus 15 into 10 power 3 pounds. Minus means our assumed direction was not correct. So P2 is in the opposite direction. It means it is a compressive force. P2 is a compressive force. Our assumption, which was tensile, is not correct. Okay. In section 3, after section 3, we can draw a free body diagram. This force P3. Summation of forces is equal to 0. So P3 is equal to, P3 minus 30, because both of them, P3 and 30 kilopounds are up in opposite direction. So P3 becomes 30 into 10 power 3 pounds, or 30 kilopounds. Here are these 3 forces, P1, P2 and P3. Okay, section 1 exists between point A and point B. So length L1 is 12 inches between A and B. Section 2 was between B and C, which is 12 inches. L2 is also 12 inches. Section 3 is between C and D, which is 16 inches. So L3 is 16 inches. L1, L2 and L3 are known. Similarly, section 1 and section 2 both have a bigger diameter, capital D, and section CD, which is section 3, it has smaller diameter, smaller d. So capital and smaller diameter both are known. We can find area from the diameter. Area is equal to pi by 4 diameter square. So A3 has been calculated from the smaller diameter, and A1 and A2 both are same from the capital diameter, from the greater diameter, bigger diameter. Okay, putting all the values in this expression, delta is equal to P1 L1 A1 E plus P2 L2 A2 E plus P3 L3 A3 E. E is same for all of them, otherwise we would have kept E1, E2 and E3 separately. So by putting all the values, E is common from here. We know all the other values. Convert load into pounds, length into inches, and area into square inches. E into PSI, pounds per square inches. So the net value of delta will be 75.9 into 10 power minus 3 inches. Remember that P2 was negative, so we have to keep a negative sign here because it is compressive. So net value of delta is 75.9 into 10 power minus 3 inches. Okay, the next example is again sample problem 2.1. The rigid bar BDE is supported by two links AB and CD. Here is a rigid bar. It means there is no change in dimensions of this bar under load. It is supported by two vertical bars AB and CD. The link AB is made of aluminum, so aluminum is not rigid. It is a deformable material. Value of E for aluminum is 70 gigapascal. Okay. It has a cross-sectional area of 500 millimeters square. So AB, area for AB is also given. Link CD is made of steel. Value of E for steel is 200 gigapascals. And cross-sectional area of steel bar CD is also given, 600 millimeter. So rod AB is actually a rectangular rod with a cross-sectional area this is cross-sectional area which is given as 500 millimeter square. Similarly for CD it is given as 600 millimeter square. There are holes here. Okay. First we have to find forces, because we know cross-sectional area, we know length of the two bars, we know E for the two bars. So if we know all of these things and we have to find delta, we just need force. Okay. For the 30 kilonewton force shown, here is the 30 kilonewton force at NE. Determine the deflection at point B, D and E. Deflection at point B is actually delta B, the change in length of portion AB. Deflection at point D means change in length in member CD. And deflection at E is a geometric deflection. We will find it after we find delta B, delta D. So we have to find how much this portion E has shifted below. We have to find it geometrically, because BDE is not is a rigid member, so there is no deformation in point E, but there is a rotation in the member, so E will move from its position. Okay. First we have to find forces in each member. Here is a free body diagram of BDE, which is a rigid member. Okay. At point B there is force AB, and point D there is force CD. Initially we have indicated both the forces as tensile forces acting away from the body. This 30 kilonewton force is given. Taking summation of moments at point B equal to 0, we can put the values 30 into its distance, which is 0.6 meters, FCD into 0.2 meters. Both the moments are in opposite directions, so one of them is with negative sign. So FCD becomes 90 kilonewton. The value is positive, So it means our assumed direction was correct. FCD is tensile. Okay. Now take summation of moments at point D equal to 0. By putting all the values, you can put the moment expression values here, values of force and values of displacement distances. So if AB becomes minus 60 kilonewtons. Minus means the assumed direction was not correct. We have assumed FAB to be tensile. If it is not correct, it means FAB is compressive. Okay. If this bar AB is compressive, it means B will move upward because A is fixed. So B will move upward. Bar CD is under tension, it means the D will move downward, and E is also moving, is displacing downward. Okay. First we have to find deformation in rod AB to find displacement of point B. Then deformation in rod CD to find displacement of point D. And from that we can geometrically calculate displacement of point E. So how we will do it? Rod AB is under compression. Area, cross-section area of the rod is already given. E of the rod is already given. Force has been calculated already, 60 kilonewton. Length is already given. We know all of the values. We can find delta B using this expression. P is actually force AB, 60 kilonewton. Okay, this is compression. So it is minus 60 into 10 power 3 newtons. Length is given, area is given, and E is given. E is in gigapascals. We have to convert it to pascals. Okay, one of the length is in meters, area is in millimeter squares. So we have to convert length, the millimeter squares into meter square. So 500 millimeter squares are 500 into 10 power minus 6 meter square. So delta B becomes minus 514 into 10 power minus 6 meter. Displacement cannot be negative actually. It can be compressive or tensile. So negative value shows compression. And definitely if there is compression, so point B is moving upward towards A because there is compression. That is why an upward sign has been shown here. Minus 514 into 10 power minus 6 meter or 0.514 millimeter. Okay. The next is displacement of point D. If we consider the member CD, it is under tension, already established. FCD is known, A is given, E is given, length is given. So after converting the units, like we have converted this millimeter square into meter squares, kilonewton into newtons, and gigapascal into pascals, we can calculate delta D, which becomes 300 into 10 power minus 6 meters or 0.3 millimeters. Since it is under tension, the member CD is under tension, so the point D will definitely move downward under tension. So a downward sign has been shown with delta D. Okay, after we know that B is moving upward and D is coming downward, so we can draw, and BDE is a rigid member, so it will not deform, but it can rotate. So it will remain straight even after rotation. B has moved upward by an amount equal to delta B, which is known. D has moved downward by an amount equal to delta D, which is known. E will come down to point E dash, and the distance EE dash, which is delta E, is still unknown. Here are three triangles. Triangle B dash BH, triangle EH E dash, and triangle DH D dash. All of these triangles are similar triangles because the corresponding angles are same. So for similar triangles, if the corresponding angles are same, the ratio of the corresponding sides will be same. Okay. Since this rod BDE has rotated, there is a point H, which is an intersection point between the new position of the rod BDH and the previous position. This intersection point is at point H. We do not know the distance of H from point D. Let us consider it as X. Since the total distance between B and D was 200 millimeter, so the remaining distance between B and H will be 200 minus X. First we have to find this X. Since these two triangles, triangle BH, B dash HB and DHD dash, since these are similar triangles, so the ratio of corresponding sides will be same. Ratio of side BH to HD will be equal to ratios of BB dash to DD dash. You know this is trigonometry. These trigonometric relationships must be known to the students. So ratios of BB dash to DD dash will be equal to ratio of BH to HD. BB dash is already known, which is delta B. DD dash is also known, which is delta D. BH is 200 minus X and HD is X. From this expression we can find X is equal to 73.7 millimeters. X is known. Now using these two triangles, triangle DHD dash and EHE dash, they are similar triangles because the corresponding angles are same. So the ratio EE dash to DD dash, ratio of corresponding sides, will be equal to the ratio HE to HD. Again, EE dash is equal to delta E, the displacement of point E. DD dash is known, which is delta D, 0.3 mm. HE is again known, it is given initially, it was 400 mm or 0.4 meters. And HD, which is X, has been found in the previous step. So by putting all the values, we can find delta E, which is displacement of point E. Point E has displaced downward, so we have shown a downward sign here. It is 1.928 millimeters. Let us move further. The next topic is static indeterminacy. Static indeterminacy means if a problem cannot, if the number of unknowns in a problem cannot be found using laws of statics, that is laws of equilibrium, by applying the equations of summation of force is equal to 0 and summation of moments equal to 0. If it is a two-dimensional problem, so we have three equilibrium equations. Summation of forces in horizontal direction is equal to 0, summation of forces in vertical direction is equal to 0, and summation of moments is equal to 0 in the given plane. And if it is a three-dimensional problem, then there will be 6 equations, 3 for forces and 3 for moments. So for a two-dimensional problem, if we have maximum of 3 unknowns, we can find them using laws of equilibrium. If the number of unknowns are more than the number of equilibrium equations, then we cannot solve it using statics. So the problem becomes statically indeterminate. Okay. A structure will be statically indeterminate whenever it is held by more supports than are required to maintain its equilibrium. In this diagram, in this figure, you can see a bar hanging at point A and supported at point B. And there are two forces, vertical forces acting on the bar. This bar is constrained at 2 points, at point A and at point B. If we remove the constraint at point B, this bar will still be in equilibrium. Either if we remove the pin support from point A, still it will be in equilibrium. So one of these support is redundant reaction. that is not required. Without support B or support A, we can still keep this bar in equilibrium. So one of them can be called redundant reaction. So whenever to solve a statically indeterminate problem, first we remove the we replace the redundant reaction with a load, with an unknown load. Redundant reactions are replaced with unknown loads, which along with other loads must produce compatible deformation. For example, this figure has a free body diagram like this one. Here for point B, at point B, we have replaced the reaction with a unknown force RB. This force RB is producing a compressive deformation in the bar because it is acting towards the bar. On the other hand, the two other forces, 300 kN and 600 kN forces, are producing a tensile deformation. So first we remove this redundant reaction and we draw rest of the diagram, free body diagram. The applied forces are producing tension, which is equal to delta L, because we have removed redundant. In the next step, we will add the redundant reaction and remove all of the other forces, like in this case, where RB is compressing back the bar by a displacement equal to delta R. Now, initially, if we see this bar is, there is no tolerance at point A and B. It is exactly fixed between A and B. There is no space to elongate for this bar. So the net deformation in this bar must be 0 because it is fixed at B and at A. So sum of these two deformations, delta L and delta R, must be equal to 0 because initially the bar was fixed between A and B. We can calculate delta L using the deformation expression derived earlier, which was P L over A E. So we can find delta L using that equation. Again, delta R can also be found using the same equation. In that case, P will be RB. After finding the two deltas, their sum will be equal to 0 because the net change in this bar is 0. So the applied forces are producing tension, the reaction force is producing, reaction at B is producing compression. It can be vice versa. A reaction can produce tension and the applied forces can produce compression. It depends upon the given loading. So using this expression, we can find at least one unknown because this is single expression. So one unknown can be found from this expression and the remaining can be found using equations of equilibrium. For that, we need to have enough number of equilibrium equations to solve the or to find the remaining unknown expressions and remaining unknown forces. I will try to solve one numerical problem example from the book on the same topic. Here's example number 2.04. The same figure is given here. Determine the reactions at A and B for the steel rod and loading shown, assuming a close fit at both supports before the loads are applied. We have to find reaction at point A and point B. Both of these reactions will be vertical. So there are two vertical unknown forces and we have only one equation for vertical forces, which is summation of forces is equal to y in vertical direction. We cannot apply moment here because both of the forces are in the line of action, the same line of action. They cannot produce moment. They are axial forces. Okay. Assuming a close fit at both the supports. So there is no space to elongate. There is no space for this bar to elongate either at end A or end B. It is closed fit. So we will move towards the solution. Before moving towards the solution, first we will treat this reaction at B, which is a redundant reaction. We will treat it as a force, as an unknown force. In the first step,
we will remove the redundant reaction like we did in this case, and we will find deformation due to the given loads. And in the next step, we will remove all the given loads and we will add the reaction force RB as an unknown force, and we will find deformation. This deformation will be in terms of RB because RB is unknown, and then we will put delta L plus delta R equal to 0 because net deformation in the bar is 0. It is a close fit between point A and point B. So let us move. First we will find delta L and then we will find delta R. To find delta L, we have to section this rod between different points. For example, it has to be sectioned between the free end and the first force, which is 600 kilonewton. The next section will be between 600 and 300 kilonewton. But then there is an area change, so we have to create another section between 600 and 300. There are two changes after 600 kilonewton. One is the force change, the other is area change. So either the force changes or the area changes, or if the material changes. In this case, the material is not changed. But if the material changes, we have to create a section and find P. Again, here, after 300 kilonewton, we have to create another section. So there are a total of 4 sections in this beam, which is like this is section 1, section 2, section 3, and section 4. Okay. So we have to find P1, P2, P3, and P4. By sectioning the bar before 600 kilonewton force, here we have to draw it separately. There is no force acting on section 1, so there is no force in section 1, P1 is 0. After that, we have to draw another section, which is section 2, this one. There is a force acting, which is 600 kilonewton. There will be a reaction force P2. Summation of forces is equal to 0. So P2 is 600 kilonewton. Similarly, P3 can be calculated. P3 is here somewhere in section 3. Sorry. Okay. So there is only single force of 600 kilonewtons. So P3 at this end will also be equal to 600 kilonewtons, because the next section, before the next section P4, there is only one force P6, which is 600 kilonewton. The next force will be somewhere here in section 4, and then here is a load of 300 kilonewtons. At section 4 there is load P4, internal force P4. Summation of forces is equal to 0. So P4 is 600 plus 300, 900. 900 kilonewtons, or 900 into 10 power 3 newtons. All these forces were tensile. I have mentioned them as a tensile forces, and the directions were tensile directions, and all the values are positive, so our assumed directions are correct. Okay, section 1 has a length of 150 millimeters, section 2, section 3, section 4. All of the sections are 150 millimeter long. Area, cross-section area, A1 and A2. Section 1 and section 2 have similar cross-section areas, and section 2 and section 3 and section 4 have same cross-section areas. Areas can be calculated, they are given. Area for section 1 and section 2 is 400 millimeter square, and area of section 3 and section 4 is 250 millimeter square. E must be same for all the sections, it is not given. So we will mention it as E, general value. So by putting all the values in the general expression, which is this one, delta 1 P1 over A1 E plus delta 2 P2 over A2 E plus delta 3 P3 A3E plus delta 4 P4 A4E. All the values are known, only E is unknown. By putting the corresponding values, we can find delta L in terms of E, which is this. Okay, delta L has been found. Now we have to find delta R. From this diagram, we have to find delta R. There is only one force, RB. Area has been changed. So we have to section this rod at two places. One is before the area change and then after the change of area. There is no other force, so there will be no other section. So this is section 1 and this is section 2. Okay. If we draw section 1, there is force RB, compressive force. So I will keep here force P1, compressive one. So P1 is equal to RB. The next section is section 2. Again, there is a force RB, and at section 2 there will be a reaction force P2. Summation of forces is equal to 0, so P2 is also equal to RB. Since this is a compressive force, so we have put negative sign with it. Okay, A1 and A2 are given in the problem. A1 is 400 millimeter square, A2 is 250. Remember that in the previous section we had in the previous bar we had 4 sections, 1, 2, 3 and 4. Diameter of 1 and 2 were same, and area of 1 and 2 was same, and area of 3 and 4 was same. In the next bar, in this bar, we have only 2 sections, 1 and 2. The areas are different. A1 and A2 are known. L1 and L2 are also known. 300 and 300 millimeter each. E is still unknown. We have to solve this problem. It's this part to find delta R, which is equal to, the previous one, this is not delta. Here is L. L1, L2, L3 and L4. Okay. P1, L1 over A1E plus P2, L2 over A2E. So we know P1 and P2 both are negative, minus RB. A1 and A2 are known. L1 and L2 are known. E is unknown. So net delta R in terms of RB and E is known. Now we know delta L and delta R. Their sum will be 0. It is already established because in the given problem it has been stated that this rod AB, this bar AB is closed fit between point A. So the net deformation is 0. Sum of delta and delta R is 0. When we put the expression for delta L and delta R is negative. In this expression, here RB is unknown. E can be omitted because anything divided by E is equal to, E cannot be 0 actually, or it cannot be infinity. So the remaining part is 0. We can take E common from here and the remaining part will be equal to 0. So we can find RB is equal to 577 kilonewtons. We will also find reaction forces at B and A. So we have already found reaction force at B. It was a statically indeterminate problem, so we couldn't use equations of equilibrium in the beginning. Now we know RB, only RA is unknown. So this one unknown can be found using equations of equilibrium. RB is known now. It is 577 kilonewton. So summation of forces in vertical direction is equal to 0. This one. Only RA is unknown, which can be found, which is 323 kilonewtons. Okay, so what we did, we just considered one of the redundant reaction, RB in this case, as an unknown reaction force. We have removed it initially and applied the calculated the deformation due to applied loads. Then we have removed the applied load and calculated deformation due to the redundant reaction. Their sum must be equal to 0. Okay. So we found one of the reaction forces, and then using equations of equilibrium, we have found another reaction force. This is how to solve statically indeterminate problems. Moving forward, our next topic is thermal stresses. Thermal, it is very clear, it is related to temperature. A temperature change results in a change in length or thermal strain. Whenever the temperature rises, there is a thermal elongation, and whenever temperature falls, there is a thermal contraction. This elongation divided by original length, or the contraction, thermal contraction divided by the original length, is thermal strain. And if we allow a body to elongate freely under temperature change, there will be no stress in the body. Free elongation doesn't produce any stress. We have to stop the elongation, and then the body will offer resistance, internal resistance. In case of free elongation, there is no internal resistance in the body. So if a body is heated up or if it is cooled down and it is undergoing a thermal strain, we have to stop this elongation or contraction. In this case, if a body of length L is taken and constrained at both ends, and then a thermal change occurs if the temperature increases, the two ends A and B are constrained and they will not allow the body to elongate. Okay, so there will be thermal stress. This problem is similar to statically indeterminate problems because the two ends are fixed. We have two unknowns, one at A and the other at B. And there is only one equation, summation of forces in x direction is equal to 0. So this is statically indeterminate problem. What we have to do, first we have to remove the reaction at point B, which is a redundant reaction. So we will remove the reaction and we will let the body elongate under thermal temperature increase. There will be an elongation of delta T, thermal elongation. The thermal elongation can be calculated as alpha delta T L. Alpha is coefficient of thermal expansion, delta T is change in temperature, the increase or decrease in the temperature, and L is length. We know it from our basic physics. This expression is known. Okay, then after that, let us remove the temperature change effect and then we add the reaction at point B due to this constant. Let me call it P. So due to P, the body will be compressed back to its original position, and let us call this deformation delta P. It is a negative deformation, delta P. Their sum must be equal to 0. So delta P can be found from this expression, PL over A E. This is already known to us. The summation of these two deformations, the net delta due to temperature change and delta due to force, constant B must be equal to 0 because net change in length in this case is 0. It is closely fit. Okay. So by putting the expressions, we can put here delta T is equal to alpha delta T L plus PL over AE is equal to 0. From this we can find P is equal to minus A E alpha delta T. This negative sign shows that P is compressive. We haven't put a negative sign in this delta P. So that is why here we can see a negative sign. If we would have kept a negative sign earlier, here the P would have been positive, and our assumed direction would have been correct. Now P is negative because it is compressive. If we divide the force by area, we can calculate thermal stress. So divide this P over area, you will get minus E alpha delta T. This is expression for thermal stress. We can solve similar numerical problems on thermal expansion and thermal contractions, and we can calculate stresses involved as a result of thermal changes, either increase in temperature or decrease in temperature. This problem is very similar to the previous one, to the statically indeterminate problem. In place of applied forces of 300 and 600 kilonewton in the previous part, here we have thermal change. So in both, the solution of both the problems will be same. We will try to solve some problems on this topic from exercise in our next lecture. I will move forward. Our next topic is Poisson's ratio. Okay. Let me assume a bar here which is subjected to an axial load P. This one. This force P is tensile, so definitely this body will elongate. So there is and it has been fixed at the other end, so the body will try to elongate. This force divided by area is horizontal stress. Let me call it sigma x. It is in x direction. There is no force on the y phase and there is no force on the z phase, either tension or compression or shear. So sigma y and sigma z are 0. So there is only one stress in x direction and there is no stress. There are no stresses in other two directions. Okay, so it means it is understood that there will be strain in s direction as well. But interestingly, there will be strain in the other directions as well. Stress is only in one direction, but strain will be in the other directions as well. Why? If we elongate this body, in this diagram you can see initially it was the dotted one, and after applying the force and after elongated it, we can see the solid body. There is a change in thickness and width in the y and z direction. We can see this is the new z and this was the old z. Similarly, change in y, this is the new y thickness, this was the previous y thickness. So thickness and width in other two directions decreased as a result of increase in the length. Similarly, if we compress this body in the x direction, this decrease in length will cause an increase in the thickness and width in the y and z directions. So stress is 0 in the y and z direction, but strain is present in all the directions. This gives rise to another concept. The elongation in x direction is accompanied by a contraction in the other directions. So in the other directions, the strain is not equal to 0. If we assume that the material is isotropic, it means the properties are not dependent on the directions. So the ratio of lateral strain, this is lateral strain. Lateral directions are those directions which are perpendicular to the axial direction. The force has been applied in the x-axis, in the x direction. This is axial direction. So the ratio of lateral strain to the axial strain. The axial strain is already known. As per Hooke's law, we know that epsilon is equal to sigma by E. Epsilon x will be equal to sigma x by E. Okay, the Poisson's ratio should be a positive value. So as we elongate the body in the longitudinal direction, in the axial direction, there is a contraction in the lateral direction. This contraction is negative strain. This is a negative strain because the contraction has happened. Similarly, in the z direction, contraction has happened. So epsilon y and epsilon z are negative. So intentionally we have kept a negative sign here. so that when the epsilon y is negative, these two negative signs will cancel out. The effect and the net value of Poisson's ratio will be positive. So Poisson's ratio is a ratio of lateral strain over the axial strain. It has no units because it is a ratio between similar quantities. Similarly, Poisson's ratio will be ratio of epsilon z over epsilon x. Z will have a negative sign and these two will cancel out. This is only possible, these two expressions are only equal if the material is isotropic. Otherwise, Poisson ratio will be different in different directions. The next topic is generalized Hooke's law. We have already studied Hooke's law for a unidirectional loading, which was epsilon x is equal to sigma x over E. But now we know that as we produce strain in one of the direction due to applied load, there will be an opposite strain in the other two directions. If the applied strain is tensile, strain in the other two directions, the lateral directions, will be compressive. If the applied strain in the axial direction is compressive, the strains in the lateral directions will be positive, tensile. So for an element subjected to multi-axial loading, as given in this figure, the normal strain components resulting from the stress components may be determined from the principle of superposition. This requires the strain is linearly related to stress and deformations are small. We can write Hooke's law for three-dimensional cases like this. The proof of this expression is beyond the scope of this course. You can do it or you can see it from your books. Strain in one of the direction is caused by the stress in that direction. If the strain is in x direction, the stress in x direction, the term with stress in x direction will have a positive sign. And then the strain in the other two directions, due to the other two directions, will have a negative sign, like these two, with a multiple of Poisson's ratio. Similarly, strain in y direction will have a positive term due to the stress in y direction and two negative terms due to stresses in x and z direction. Similarly, strain in z will be caused by three stresses, sigma z with positive sign and sigma y and sigma x due to with negative signs. So these three expressions will be used in all three-dimensional problems related to stresses and strains. You do not need to prove this expression, and if you want to prove, you can see the proof of this expression from your book. I do not want to discuss it in detail. Okay. Our next topic is dilatation and bulk modulus. What is dilatation? Dilatation is defined as change in volume per unit original volume. It is a volumetric strain actually. Dilatation is equal to, if it is represented with E, it is equal to change in volume per unit volume. Okay, if you assume a cube with the unit volume like this one, the three sides are 1 cross 1 cross 1, so the net volume is 1. After applying stresses sigma x, sigma y and sigma z, the new dimensions of the sides are 1 plus epsilon x, 1 plus epsilon y and 1 plus epsilon z. So the new volume will be 1 plus epsilon x multiplied by 1 plus epsilon y multiplied by 1 plus epsilon z. The product of the sides of this cube. Okay, this is new volume. The previous volume was only 1 initially. It was, and the sides length, each side has a length of 1. So the change in volume, final volume minus initial volume, divided by initial volume, which is 1. This is equal to dilatation E. Okay. if we simplify it, this expression, if we open the multiplication terms, there will be some terms involving product of epsilon x and epsilon y and epsilon z, and similarly epsilon x and epsilon z, and some products will be involving 3 strands. The product of strain is generally a very small number, so the product of 2 or more than 2 strands will be very small. So we will neglect the terms involving product of 2 or more than 2 strands, and we can simplify this expression. Dilatation E will be equal to epsilon x plus epsilon y plus epsilon z. This is dilatation, or change in volume per unit volume. If we put epsilon x, epsilon y and epsilon z in terms of sigma x, sigma y, sigma z, nu and e from the Hooke's law expression, generalized Hooke's law, let us put these 3 expressions of epsilon x, epsilon y and epsilon z from here in this expression, and then we simplify it. We can get E equal to 1 minus 2 nu divided by E into sigma x plus sigma y plus sigma z. So this is expression of dilatation in terms of stresses, sigma x, sigma y and sigma z, and the previous one was in terms of strains. We can use any one of them. It depends upon over the known value. Either we know the values of stresses or strains. Okay. If we move, you can do these calculations by yourself, the simplification steps by yourself. Now, let us assume an element subjected to uniform hydrostatic pressure. So let me assume an element subjected to uniform hydrostatic pressure. Hydrostatic pressure is constant from all the sides, and it is always a normal force. Like if you keep a body in water, the water will exert equal pressure from all the sides, and it will be only normal force. There will be no shear force. So let us assume a hydrostatic pressure on a body. So sigma x, sigma y and sigma z, all of them are equal to minus p. It is compressive. So by putting sigma x, sigma y and sigma z equal to minus p in the above equation, we can write dilatation equal to minus 3p into 1 minus 2 nu divided by E. All the terms involved in this expression except P, pressure P, are constant. E is constant, it is modulus of elasticity, it is a material property. Nu is Poisson's ratio, it is a material property, it is constant. The other terms are digits like 1, 3, 2, they are all constant. So this term is a constant term. So let us call E by 3 into 1 minus 2 nu equal to K, small k. This is bulk modulus. So here it is 1 over K, it becomes minus P over K. K is bulk modulus, and bulk modulus is resistance to volumetric change. The physical meaning of bulk modulus is resistance to volumetric change, volumetric strain. Okay, so now E is equal to volumetric strain is equal to dilatation is equal to minus P, P is hydrostatic pressure, over K, K is bulk modulus. Here it is. Okay, since this change in volume must be negative because this body is under compression, so the net value of E must be negative. if the value of E is negative, it means this expression is already minus P over K. So it means K should be positive. If K is positive, K is equal to E over 3 into 1 minus 2. No. If K is kept positive, it means 1 minus 2 no should be positive. Should be greater than 0 because E is already positive. 3 is a positive multiple. So 1 minus 2 no should be positive. This means no should vary between 0 and 1 by 2. If no is greater than 1 by 2, then this value can be less than 0 and this term can be negative. So in order to satisfy this condition, or in order to keep the value of K positive, no should vary between 0 and 1 by 2. So the value of Poisson's ratio cannot exceed 1 by 2 and it cannot be less than 0. Okay, so this is whenever we use Poisson's ratio, you have to keep in mind that Poisson ratio cannot be less than 0.5 or 1 by 2. Okay, our next topic is shearing strain. We have already discussed normal strain in enough detail, and now we are moving towards our next topic, which is shearing strain. So in terms of normal strain, previously we have discussed that normal strain is a change in length, either increase in length or decrease in length per unit original length. Shear strain is not a change in length. It is not related to change in length. It is related to change in angles of the sides. For example, we have a cube here and shear stresses are being applied on the sides of the cube like tau xy, tau yx and tau xy. These shear forces or shear stresses will convert this cube into a rhomboid. The angles of the sides have been changed. Initially these angles were 90 degrees. All the angles were 90 degrees. Now, if we look at this face only, the front face, the xy face, we can see two of the angles have decreased. They are pi by 2 or 90 degree minus gamma, and two of the sides have increased by the same amount, which is pi by 2 plus gamma. Increase in the angle of one of the side, two of the sides is equal to decrease in the angle in the other two sides, between the other two sides. Okay, we know that stress is a function of strain. So shear stress is a function of shear strain. This is Hooke's law as well. And this function is actually dependent upon a constant value. Hooke's law is like this. Shear stress is proportional to strain in the elastic limit only. So for small values of strain, we can say that shear stress is equal to G into gamma. G is modulus of rigidity. Similar to the previous one, we had normal stress equal to E into strain, where E was modulus of elasticity. Now shear stress is equal to G into shear strain, and G is modulus of rigidity. Okay. A plot of shear stress versus shear strain is similar to the previous plots of normal stress and normal strain, except that the strength values are approximately half. So a stress strain diagram for shear stress and shear strain, gamma and tau, it will be similar to that of normal stress and normal strain for ductile materials and also for brittle materials. So the shape of the curve is similar to that of curve of normal stress and normal strain. We also have tau yielding and tau ultimate here. But important thing is the strength values are approximately half. This tau y shear yield strength is almost half of sigma y. Similarly, ultimate shear strength is almost equal to half of ultimate normal strength. Rest of the shape of the figure is diagram is almost same. There is a numerical problem, a solved example from the book on the topic of shear strain. This is example 2.10. A rectangular block of material with modulus of rigidity equal to 90 ksi. G is 90 ksi. It is bonded to two rigid horizontal plates. You can see here. Here's a rectangular block. It is bonded to two rigid plates, this one and this one, from the top and the bottom. The lower plate is fixed. This lower plate is fixed to the ground or whatever, bottom, while the upper plate is subjected to a horizontal force P. So force P has been applied on the upper plate. Okay. Knowing that the upper plate moves through 0.04 inch under the action of the force, this plate moves in the direction of the force. How much does it move? It moves by 0.04. I think it is 0.04. Yes, 0.04 inch in the direction of the force. Okay, the bottom plate is fixed with the ground, so it will not move definitely. The upper plate will move the upper part of the block with itself. In part A, we have to determine the average shearing strain in the material. We have to find gamma, average shearing strain. The part B is the force P exerted on the plate. Force P we have to find. If we look at the two-dimensional view from this side, we can draw it as a rectangle. This box is a rectangle and it is connected to two rigid plates. The rigid plates do not suffer any kind of deformation. If force P has been applied here, this plate will deform like this. Okay, so this distance is, this deformation length is 0.04 inch and the vertical height is already given. It is 2 inch. So from this triangle we can find gamma. 0.04 inch, this is 2 inch. So here we can find gamma, or tangent gamma, it is equal to 0.04 divided by 2. From right angle triangles we can find angles very easily using our trigonometric relationships. For small angles, strain is usually very small number, either it is normal strain or a shear strain. So for small angles, tangent of the angle and angle itself are almost same. In radians, remember that 0.02 radians and tangent of this 0.02 radians will almost be equal to 0. Almost will be equal to each other. In the first part, we had to find shear strain and which has been calculated. In the next part, we have to find force P. For force, we need stress because stress is equal to force by area. So area is already known. We need to have stress. So from strain, we can find stress. Shear stress is equal to G into shear strain. G is given in the problem, which is 90 into 10 power 3 psi. So 90 into 10 power 3 psi multiplied by radians, 0.02 radians. So the value of shear stress is 1800 psi. Load P is equal to shear stress into area. Shear stress is known, 1800 psi. Which area we have to take? It is shear stress. So the shearing area, the area which is parallel to the load, or the sliding area actually. Which area is parallel to the load? This area. And this is actually the common area between the top plate and this box. Here we can see this block. Here we can see this plate was rigid. Area between this rigid plate, the common area between the rigid plate and this block, which is parallel to the force and which is sliding upon each other. So this area is 8 inch into into 2.5 inch. 8 into 2.5 is area. The stress is 1800 psi. Their product is 36 into 10 power 3 pounds or 36 kilopounds. These two values were required, shear stress and load, and they have been calculated easily. Okay. Our next topic is relations among E, which is modulus of elasticity, nu, which is Poisson ratio, and G, which is modulus of rigidity. Here is a rectangular bar under load P. Initially, if we specify a cube, which is dotted one here, cube of length 1 into 1 dimension, 1 cross 1, and we apply force, axial force on it, we will see that there will be change in length of this cube. In the one direction it will be increased, in the other direction it will be decreased. The increase is 1 plus epsilon x, and the decrease is 1 minus nu times epsilon x, or it can be 1 minus epsilon y. So since epsilon y is unknown to us, we can write it as nu into epsilon x. Okay. Because there is no force in the vertical direction, so all the deformations in the vertical direction will be due to this horizontal force. So we have to use nu here. Okay. This rectangle, initial cube element has been converted into a rectangular parallel piped. Okay. So this axial load has produced normal strain, which strain in the axial direction, and in the vertical direction it has produced normal strain, tension and compression. Okay, if this instead of this cube, if we have the same cube in another orientation like this dotted one, and we apply force on it, we can see there will be a change in angle of the sides of this element, this cubic element. So this cubic element has been converted into a rhombus. So the axial force has resulted into a shear strain. In the previous case, the axial force has resulted into normal strain. Now it has resulted into a shear strain, change in angle. You can see that the angle has reduced at this edge and it has increased here by an amount of gamma. Initially it was pi by 2, now it is pi by 2 plus gamma and pi by 2 minus gamma. So it means the normal forces may produce shear stresses and shear strains. Similarly, normal force may also produce normal stress and normal strain. There is a relationship between the constant values involved in normal loading, normal loading and shear loading. E is involved in normal loading, nu is involved in normal loading, G is related to shear loading. So E, modulus of elasticity, G, modulus of rigidity, and nu, the Poisson's ratio, have a relationship which is shown here. E over 2G is equal to 1 plus nu. You can see the derivation of this expression from your book. Here I have just to introduce this relationship. We will use this relationship between E, G and nu in our numerical problems whenever value of two of them is given and the third one is unknown or it is required, so we will use this expression. Usually the values of E and nu are given, and if you want to find shear strain or shear stress, you need G, and you can calculate G from this expression. Okay, we'll move further. On the next slide, we have a sample problem, which is sample problem 2.5. A circle of diameter 9 inches is scribed on an unstressed aluminum plate of thickness equal to 3 by 4 inch. Forces acting in the plane of the plate later cause normal stress of 12 ksi in x direction, and z in the z direction it is 20 ksi. So this plate, dimensions are given 15 into 15. The thickness is given, which is 3 by 4 inches. Diameter of the hole is given, which is 9 inches. The plate is stressed up in x and z direction. Sigma x and sigma z are also given, 12 ksi and 20 ksi. The value of E is given, modulus of elasticity, it is 10 to 10 power 6 psi. Nu is given, which is 1 by 3. Determine the change in the length of diameter AB. This one, change in length of diameter AB. So we have to find strain in x direction. Diameter AB is in x direction. For this change in length, we need epsilon x. Remember it. Change in the length of diameter CD. Diameter CD is in z direction. For this change in length, we need epsilon z. Okay. This change in diameter is a separate one. Change in diameter is not directly strain, but we have to find strain, and then we can, from strain, we can find change in length. Diameter is a kind of length, so remember it. Okay. The thickness of the plate. Thickness is in y direction, so we need epsilon y. And the final one is change in the volume of the plate. So total volume, we can find total volume from dilatation, change in volume from dilatation. So first we need to find these three strains. How would we calculate these three strains? We have three stresses, sigma x, sigma y, and sigma z. Sigma x is given, it is 12 ksi. Sigma z is given, it is 20 ksi. Sigma y is not given, but there is no force visible in this diagram in the y direction, so sigma y is 0. We know all these three stresses. We know nu and we know E. We know all these values. We can use Hooke's law, generalized Hooke's law, to find normal strain. So generalized Hooke's law is given for epsilon x, epsilon y, and epsilon z. All these values are known: sigma x, sigma y, sigma z, E, and nu. By putting the relevant values, we can find epsilon x, epsilon y, and epsilon z. The unit is in inch per inch, so there is actually no unit of normal strain. Epsilon x is positive, definitely it should be positive. It is sigma x was tensile. Epsilon y is negative, epsilon z is positive. So this plate has been stretched up in x and z direction. So definitely in the third direction it will compress. So we have found the three values of strain. Now direction AB, the diameter AB is in x direction. We know that strain is equal to delta divided by length. So epsilon x is equal to change in AB divided by length of AB. Length of AB is actually diameter AB. Diameter is known. Diameter AB and CD both are same because it is a circle. So AB or CD diameter both, they are 9 inches. So we will use this expression. Delta AB or delta BA is equal to epsilon x into diameter. We know epsilon x from our previous step, which is 0.533 into 10 power minus 3, and diameter is 9 inches. So delta AB or delta BA is calculated. Similarly, delta CD, change in the diameter in the z direction. So it will be epsilon z is equal to delta CD divided by DCD. DCD or DAB both are same. So by putting the values, delta CD has been calculated. It is 14.4 into 10 power minus 3 inches. Thickness is in y direction. Here we can see. So thickness can be calculated from epsilon y. It is change in thickness divided by actual thickness. So change in thickness has been calculated. It is negative because epsilon y is negative. Definitely there is a compression, so change will be negative. So the first part has been solved. We have found these three changes. At the end, we were asked to find, these were the first three parts, A, B, and C. At the end, we were asked to find change in volume, total volume. For dilatation, delta E is equal to change in volume per unit volume. Dilatation is equal to sum of the three strains. We have already derived this expression. The three strains are known to us. Here we have calculated them. By putting the values, we can find dilatation. And change in volume is actually equal to E into volume, original volume. E is known. Original volume can be found from the product of the sides, lengths of the side, 15 inch into 15 inch into thickness, which is 3 by 4 inch. So 15 into 15 into 3 by 4. 3 by 4 is actually 0.75. So we can find change in volume in terms of cubic inch, which is 0.187. Okay, it is a positive value. It means the net volume has increased. Okay, we will move further. Our next topic is composite materials. Composites are actually tailor-made materials. We can induce our required properties, the properties we need in a material, in the composite materials. They are not naturally occurring materials. They are made by human beings. Composites are made from more than one type of materials. The basic ingredients of composite materials are reinforcement and resin. Reinforcement is usually in the form of fibers. You can see here these fibers, dotted dots here. These are fibers inside a matrix. Inside this matrix, fibers have been reinforced. You can see the side view here. A very good example of a composite material is concrete and steel used in columns and beams in construction of different buildings. Steel is a fiber, steel rods are fibers, and the concrete is a matrix or a resin. We can find properties, different properties in different directions. Sorry. Okay, so fiber reinforced composite materials are formed from lamina of fibers of graphite, glass, or polymer, or even metals embedded in a resin matrix. So I have given you an example. The steel rods are fibers and they are embedded into a ceramic matrix of concrete. Normal stresses and strains are related by Hooke's law, but with directionally dependent moduli of elasticity. Hooke's law is applicable on composite materials in the elastic region, but the properties of composite materials are different in different directions. They may be sometimes same in some of the directions, but Ex, modulus of elasticity in x direction is equal to sigma x by epsilon x. Similarly, modulus of elasticity in y and z directions are also different. They are equal to sigma y over e epsilon y and sigma z over epsilon z. Similarly, Poisson ratio is different in different planes. Transverse contraction are related to directionally dependent values of Poisson's ratio. So Poisson's ratio in xy plane will be equal to epsilon y over epsilon x. Poisson's ratio in xz plane will be equal to epsilon z over epsilon x if the applied force is in x direction. Materials with directionally dependent mechanical properties are anisotropic. Since the composite materials have directional dependent properties, E and nu are different in different directions. So such kind of materials are called isotropics. This is the definition of isotropic material, to have different mechanical properties in different directions. Okay, our next topic and a very important one. It is Saint-Venant's principle. Okay. Usually, when we apply point loads, point forces, they produce deformation, very large deformations at the point of application of force. Here in this diagram, you can see rigid plates at the two ends. If a force is applied through rigid plates, the rigid plates will compress the body equally through the width. The loads transmitted through rigid plates result in uniform distribution of stress and strain. But if a concentrated force is applied like this one without a rigid plate, there will be large stresses in the vicinity of the load application point. At the load application point, there is a large strain, large deformation, and then it slowly dies out up to the edges. So in the load vicinity point, there is stress concentration. Okay, the stress and strain distributions become uniform at a relatively short distance from the load application point. If we see here, load is applied here and we go along the length. As soon as we move from the surface of load application, stress is distributed. There is a minimum value of stress and there is a maximum value of stress, and there is a huge variation between minimum and maximum values of stress. If we go further, this thickness was this length was 1/4 times width. This is width B. Okay, now if we go further at a depth of 1/2B, again this is B, the variation between sigma minimum and sigma maximum will be little lower. And if we further move till a depth of B, the minimum and maximum stresses are almost same. Here's the relationship. Sigma minimum is 0.9 times sigma average. Sigma maximum is 1 times sigma average. So 0.9 and 1.0 are almost same. Sigma average is actually B over A, which we are consistently using. In this case, where depth is 1/2B, sigma minimum and sigma maximum have a difference 0.6 and 1.3 times sigma average. Further, at very small depth 1/4 times B, there is a big difference between sigma minimum and sigma maximum, 0.1 times sigma average and 2.5 times sigma average. It means as soon as we move away from the point of application of force or surface of application of force, the effect of stress concentration dies out, and the difference between maximum and minimum stress decreases. These two values of maximum and minimum becomes almost average values at a distance of B, or a distance equal to width of the plate. Now we have a principle here, Saint-Venant's principle. The stress distribution may be assumed independent of the mode of load application except in the immediate vicinity of the load application point. So immediate vicinities of load application points are very important. Beyond the immediate vicinities of load application point, the stress is independent of the mode of the load. Okay, either it is a point load or a distributed load. If we move away from the load application point, stress is almost average. Now we have some special cases to be discussed here. If we have a plate and there's a hole inside in the center of the plate, and force is being applied at the ends of the plate, we note that the maximum stress will exist around the hole because hole is stressed up. It will be maximum where the diameter of the hole exists. These parts are stressed up. So we can see in this diagram there is stress on the solid surfaces. This stress will never be uniform, it will never be constant throughout the surface. It will be maximum at some point and minimum at the other points. So at sharp edges it is maximum, and at the other end it is minimum. How we can find the maximum value of stress? Maximum is important for us, minimum is not important. So here is a diagram. Before that, I want to introduce a term which is stress concentration factor, K. The stress concentration factor is equal to ratio of maximum stress to the average stress. Average stress can be calculated from this expression P over area. K can be found from this graph. So we can find sigma maximum for this configuration of a plate having a hole and loads being applied at the ends of the plate. In this graph, you can see horizontal axis is small r by d. Small r is radius of the hole. Small d is equal to capital D minus diameter of the hole divided by 2. So small d is equal to capital D minus diameter of the hole, which is 2r divided by 2. Here you can see this is half of d. So definitely it can be calculated using this expression. So for your information, in the numerical problem, all these dimensions will be given, P will be given, and you can find sigma maximum like this. And if sigma maximum is given, you can find P. Another special case is fillet. How to find stress concentration at fillet? So here are fillets of radius r. This will also be r. There are two widths, capital D and small d. You can see stress will be maximum around the fillet point and it will be minimum in the center. We can find average. Again, the same expression can be used. K is equal to sigma maximum over sigma average. Sigma average is equal to force by area. Here we have curve for this case. Smaller radius of the fillet. Small d is width of the smaller portion. Capital D over small d ratio is given. Capital D is width of the bigger portion. And here is K. So if we know the values of R, capital D and small d, we can find this ratio and this ratio from the corresponding. For example, D by D ratio is 1.5 and R by D ratio is around 0.08. So 0.08 and the curve of 1.5 is this one. This value is almost 2.4. So we can find the value of K, which is 2.4. We can put it in this expression. We can find sigma average from this expression. Sigma maximum can be calculated. We will use this method to solve an example problem on the next slide. Okay, here's an example problem number 2.12. It states as, determine the largest axial load P that can be safely supported by a flat steel bar. Flat means it is rectangular, it is not round. Consisting of two portions. One portion has a width of D, small d, the other one is capital D. Here is radius of fillet, which is small r. Both 10 mm thick. The thickness of the bar in third dimension is 10 mm. So we can find cross-sectional area. And respectively 40 and 60 mm wide. So small d is 40 mm, small depth, small width, capital D is 60 mm. Small r is given as 8 mm. Assume an allowable normal stress of 165 megapascal. So allowable stress. Allowable means this is maximum value. we cannot apply more stress than allowable stress. So we will assume it as sigma maximum. Or applied stress cannot exceed allowable value. So sigma maximum is known to us. We have to find P. P is, determine largest load P. P is equal to sigma average into area, because sigma average is equal to P over area. So we have to find sigma average. Area is already known. Sigma average can be found from this expression, sigma maximum divided by K is equal to sigma maximum divided by sigma average. Okay, so K can be found from the graph, from the curve given in the literature. Remember that they have mentioned here to find largest axial load. So I will explain what is largest axial load. Let us move further. First, we find ratio of capital D over small d. They are given capital D and small d 60 over 40, so it becomes 1.5. Ratio of R over small d 8 over 40, it is 0.2. So 0.2 and 1.5. We can find the value of K from the graph at 0.2 and 1.5. This is R by D equal to 0.2, and here is a curve of 1.5, so it is almost this value. This value of K is around 1.82. You may judge it as a 1.83 or 1.81, so it depends upon you. It is almost close to 1.82. If we know the value of K, we can find from this expression the value of sigma average. Because sigma maximum is already given, it is 165 megapascal. K has no units, so sigma average will be 90.7 megapascal. Now, load is equal to area into stress. Which area we have to take? One is this area, and the other one is this area. So we have to take the smallest area, because at the smallest area the stress is maximum, and maximum stress is always important for us. So this smallest area is 40 mm into thickness. Thickness is, I guess it is 10 mm. Yes, it is 10 mm. So 40 into 10. So area is 40 into 10, and average stress is, already it has been found, 90.7 megapascal. So P becomes 36.3 into 10 power 3 newtons, or 36.3 kilonewtons. It is largest allowable P, because we have taken the smallest area. From smallest area we can find the largest stress, and that largest stress is caused by largest force P. So we can find P from it. You cannot take this greater area in this calculation. You have to take smaller one, so that we can find the larger stress. I hope you will understand this topic, and I advise you to solve some example problems and exercise problems from the book on this topic. It is very important. Stress concentration. Okay, our next topic is elastoplastic materials. Previous analysis based on assumptions of linear stress-strain relationship, that is stress below the yield stress. Assumption is good for brittle materials which rupture without yielding. But if the yield stress of the ductile materials is exceeded, the plastic deformation occurs. For brittle materials, in the brittle materials generally there is no yield stress. The brittle materials fail like this. They directly fail due to rupture, due to ultimate stress. But in ductile materials, after yield stress, there is a permanent deformation. So at point B, there is yielding, and after point B, the material still exists. It is not fractured, but there is permanent deformation. if we unload the material beyond the yield strength, beyond the yield stress, like at point C we unload the material, so it will recover here, but at point D the value of strain is not zero. There is some strain inside the material. Even though the load is zero, stress is zero. If we further unload or if we apply a compressive force, so it will deform in the negative direction. You can see this curve. After certain value of compressive strain, if we further apply tensile force on it, a tensile load on it, it will again start elongating. The slope of this line and this line are almost same. Okay. Similarly, if we unload this material from another point, which is C dash, it is also in the plastic region. Again, it will recover till point D dash, but there is a positive strain in this material. The strain is not zero. So if we remove the load from the material in the plastic region or in the permanent deformation region, the material will recover up to certain point, but there will be no full recovery. The net strain will not be zero. There will be some non-zero strain in the material. And if we further apply compressive stress on compressive load on this, it will again make another curve. This is permanent deformation. Again, if you apply axial load, tensile load, it will again deform in the tensile direction, and it will touch this curve again. So loading and unloading of a material from the plastic region may induce some permanent stresses and permanent strains in the materials. These permanent deformations result from loading beyond the yield stress. Any material loaded beyond the yield stress will be permanently deformed, and after permanent deformation, unloading the material will not make it will not cause it to recover to original position or original shape. So after plastic deformation, the materials will never come back to their initial shape or initial length or initial position. Repeated loading and unloading may be a kind of fatigue phenomena, and the materials may finally fail even before sigma ultimate. Okay, this constant loading or unloading of material beyond the yield limit will produce some positive or negative strain in the material. The strain will not be zero in such case. That non-zero strain in the material is called residual strain. Residual strain exists in a material in the absence of external load. This strain is caused by loading and unloading the material beyond the yield limit. So there is a permanent strain in the material which is called residual strain, and this residual strain causes a residual stress in the material. So residual stress is a kind of stress which exists in the material in the absence of load. Currently there is no load, but earlier the material was loaded beyond its yield limit and then it was unloaded. That is why there is some permanent stress in the material. So residual stress is can be discussed here. It is when a single structure element is loaded uniformly beyond its yield stress and then unloaded. It is permanently deformed, but all stresses disappear. This is not general result. If we think stress is equal to force by area, and we generally assume that when we unload a material from the permanently deformed region or permanently deformed point, we think if stress is zero, if load is zero, so stress should be zero, but it is not the general case. This will be a case if the material is unloaded before the elastic limit or before the yield stress. But if a material is allowed to deform permanently and then the load is removed, so the net stress will not be zero. Residual stress will exist. Residual stresses will remain in the structure after loading and unloading if only part of the structure undergoes plastic deformation. So after plastic deformation, you cannot make stress equal to zero. Different parts of the structure undergo different plastic deformations. So it doesn't mean that the whole structure will have same amount of deformation, same amount of stresses. Residual stresses also result from uneven heating and uneven cooling of structures or structural elements. So sudden cooling, sudden heating, or uneven heating and uneven cooling also result into the residual stresses into the materials and structures. So it is recommended to heat up or cool down materials constantly, not suddenly. Residual stresses may cause failures or may cause decrease in the performance of structures. So always it is recommended not to load up a structure beyond its yield strength, because whenever you will load up a structure beyond its yield strength, there will be permanent deformation in the structure, and after unloading, that permanent deformation cannot be restored and the material cannot come back to its original position. So there will be some permanent strain and permanent stresses in the material, which are called residual strains and residual stresses. This was the last topic of this chapter. We will solve some exercise problems from this chapter in our next lecture. I hope the topics discussed during this lecture are understandable, and if you have any point to discuss or if you have any query, you can send me an email and I will try to answer you. Thank you.